some remarks about the, oh, there it is, about flat virtuals and what we were doing before. So let me review this from the beginning and show you what new I can say about it. So you'll recall that we have this method of labeling the flat diagram, and then we were using the label of the flat diagram to compute an invariant of virtual knots that could lie over that flat diagram. But now I'm interested in what information I can extract just for flat virtuals from the same table of information. So let's remember how it goes. If you have a classical crossing flat, then you index by going up by one if the cross line goes to the right, and down if the cross line goes to the left. Once it's labeled, you take the difference between the left incoming line and the right outgoing line above for the W plus, and the difference between the left incoming, right outgoing below for the minus. They are negatives of one another. So here is an example. I have this flat, and I have labeled it accordingly, and I find that my weights are as indicated in this table for the crossings A, B, and C that are real here. And as you see, they're all non-zero in this case. Now, if I take a reversed version of the knot, like I have actually done it here, I took D and I reversed it so that all the arrows go in the opposite direction, and I make my computation. Well, what will happen is that the two columns will reverse. That is, here you had 1, 1, minus 2 in the plus domain and minus, minus 2 in the negative domain. Those flip, as you see here. You'll get the W plus column will be negatives, and the W minus column will be the ones that were in the positive columns. You flip the columns. So if I define, so then I have this elementary proposition that the weight table for the reversed diagram is W hat, where W hat is the one with the columns interchanged. And the proof of this is something that we did before, but we were saying it for the invariant lying over. So I just thought I'd remind you again how it just comes from the weights that we're computing. Um, um, what I have indicated here is calculating the weight by looking at the difference across a crossing of taking the looking at what happens when you go all the way around a loop and come back, and then that difference is the weight, and you can then see what would happen if there is a total change that occurs. And if there is a total change that occurs, then it will be as though it were in some direction. But when you reverse it, everything is reversed, right? So these arrows reverse and this direction reverses. And then you look at what happens to the weights by doing a simple calculation, and you find that they reverse. So that's the proof that the weights reverse in that way. And then the other facts about these weight system is that under the rise through 3 move, the weights do not change at all. If you relabel as I have indicated here, you get the same weights, just a little permutation of the labels for the crossings. And then under the 2 move, if you look and ask what happens in the table, you will see that you will either add or remove a little submatrix in the table of the form M and minus M and minus M and M. We did this before, but I'm just reminding you. And these notes will be part of this last lecture so that it'll all be together in one piece. So the table does change, but it changes in a very special way. You not only get a row, but you also get the negative of that row. And then for for a loop, a one move, you get a 0 row. Okay. So that means that if we took the tables modulo um, modulo submatrices of this kind and modulo 0 rows, then that would be an invariant. We can say this in a more polynomial way in a moment, but that would be an invariant. And we can deduce things just from thinking about the table. So, so what can we say? The property that the weight table is not equal to its hat, that um, that when you interchange the rows, you get something different. That's invariant under Rademeister moves and detour moves. The the point is that a second Rademeister move doesn't perturb that because in a second Rademeister move, this matrix is invariant under interchanging the columns. So if the weights table is not symmetrical under column interchange, then that's invariant under Rademeister moves. And so that means that if the weight table is not symmetric under a column change, then the flat link is not equivalent to its reverse. So we have a rather strong consequence of thinking about the weight table about reversing. Um, and this is interesting to a classical knot theorist because in classical knot theory, it's actually very tricky to prove classical knots are inequivalent to their reverses. In virtual knot theory, it's much easier in many cases, and it's this sort of phenomenon that is actually in back of that. Then, in the example that we had, we certainly can conclude that this example and its reverse are distinct. And you'll recall that we could do this for knots that lay over these by the nice formula that pk reverse of t is pk of t inverse. And that is actually following immediately from our result about the tables, if you think about the definition of pk, which we're not focusing on today, the affine index. On the other hand, I can define a polynomial invariant very easily here. I simply take the sum over the crossings of t to the w plus of that crossing minus t to the w minus. In other words, for each row in the table, I take t to the entry here minus t to the entry here. So that means that the polynomial I pick up here is going to be t minus t inverse, t minus t inverse, t to the minus 2 minus t squared. And if you think about that for a moment, everything we said about the tables shows you that this polynomial will be invariant. 0 rows are not seen by the polynomial. If you had a row of the form 1 minus 1 minus 1 1, for example, well then whatever this contributed, the other one with the flipped signs would cancel it out. So this is invariant polynomial. And so we have that it's an invariant of flats. There's where I said that. Okay, you see, think about what that will do to the polynomial. You'll get t to the n plus t to the minus t to the minus n plus t to the minus n minus t to the n. It all cancels out. The q on a diagram of t inverse is then equal to minus qd of t by our definition, because this is minus that, and if you put in t inverse, it just flips and becomes minus. So that means that if qd of t inverse is not equal to minus qd of t, well then, and in other words, if qd of t is not equal to 0, then d is not equivalent to its reverse. And QD reverse of T is, of course, QD of T inverse. So we have these nice properties of this polynomial. And the polynomial summarizes all these observations that we have made. So in the case of the example that I had here, QD is 2 T inverse minus T minus T inverse and T minus 2 minus squared. Well, there's another thing you can see here. Every time you get a crossing which has a non-zero row, then it contributes something to the polynomial. right? Um, and and so as long as you have um, as long as you have no little submatrices of this type, those will all add up. So you can conclude that if there are no submatrices of this type and you have non-zero crossings, then you can find the number of crossings in the diagram directly from adding up the coefficients of the polynomial. And more generally, the sum of the coefficients of the polynomial will be equal to less than or equal to the number of crossings in any diagram since it's invariant. So if you only saw the polynomial, you could conclude that the number of crossings is less than or equal to 3, number of real crossings. And in this case, it really is 3. In other cases, it's a lower bound. Um, on looking around after seeing this, I discovered that in a paper by Chang in the archive, he observes that the difference between the affine index and the affine index of T inverse is a flat invariant, but he didn't observe the other things that we are talking about it. What I've described and called Q is actually exactly this, if you think about it. But we don't have to go up to invariance of virtuals to get it. It is simply this very simple formula on our weight table. Now let's see what else we can say about it. Oh yeah, it's a concordance invariant for flat virtuals. We talked a couple of weeks ago about how P was a concordance invariant for virtuals, and all the same proofs work, and it is a concordance invariant for flat virtuals. I will be thinking about this and writing a paper about what I'm talking to you about now, and I probably will send it around to the list in a couple of weeks when the paper is available. And there will be some other facts that will be interesting about this. Here's an interesting little phenomenon, never mind the rest of the slide. Here's the Kishino diagram, and um, it has a zero Q polynomial. Um, but that's neither here nor there. It is definitely non-trivial, but I'm thinking about concordance of flats. And you might wonder, well, this is an irreducible diagram. We know this is a least diagram for this, and it probably is not equivalent to its reverse. My guess. But I don't have a proof that it's not equivalent to its reverse um, because the Q vanished. On the other hand, notice that it is concordant to a trivial knot, as we must have observed back. We go through a saddle point here and it falls apart. So it's concordant to a trivial one. And so the trivial one is reversible. So we have a conjectural example here of an irreversible which is concordant to a reversible. I am sure that using Q, I could make an easier example that was fully rigorously shown to have that property, but I haven't done it. Um, then there's a, the possibility of using Katakami's results, which I mentioned before, this interesting paper by Katakami. What Katakami showed was that any flat virtual knot has a minimal genus diagram in the sense of a surface on which it can be drawn, like this surface here. Um, a minimal genus diagram that it can be obtained by reducing the diagrams by moves, and that if D and D prime are two minimal genus diagrams, then flat diagrams for minimal genus, then they would be related by only R3 moves. So this this fact that the R3 moves leave Q alone, and the fact that R3 moves are the only thing that happen at minimal genus are very interesting things to compare. I'm going to say another word about Kami once I take up my pencil, but we can ask some questions, and I won't worry you about them. Just include this part of the slides. Here's another example. Now, this example is an obvious generalization of the one I did before. I just added two more crossings, and then I have every other crossing is a virtual, and so I have five rather than three, and I label it, and I find that once again I get a completely rigid table, no cancellations in this table, and that means that I can conclude that the crossing number for this flat diagram is in fact equal to 4. And that's because it realizes 4 and it can't be less than 4. And this therefore should be a minimal diagram. Now, does minimal crossing number imply minimal genus diagram for flats? I think this may be true. It may be possible to prove this by Monturov type parity projection. We can check. We didn't talk about this. So you might conjecture at this point. In any case, this is definitely a minimal diagram in the sense of crossing number. And we can check genus in the way we have done it earlier in the course. Remember how we check the genus of a diagram? We construct the ribbon surface for it. And then we use the fact that the genus is equal to the number of crossings minus the number of boundary curves, which we'll be filling in by disks, divided by 2 plus 1. So it says genus 2. Incidentally, Katakami observed in one of his papers, you might take as an interesting exercise, that no virtual flat that's non-trivial can have genus equal to 1. It would have to have genus higher than 1. But getting back to this example, as you see, this is a good example in that the pattern is clear, and we could add another one and another one and another one, and we have an infinite collection of diagrams here, all of whom are minimal, all of which have non-trivial polynomial and so on. So all of which are not equivalent to their reverse. So we have a class of infinitely many flat diagrams inequivalent to their reverses. So I think that this is interesting to think about, to just concentrate on questions about flat virtuals in this way. And there's more to be done here, and more will be done. There's a level below this, which we didn't discuss in the course, and I think I should mention it, but I'll go into my scribbling now, if I can find my pad. Yeah. So we have virtuals, and then we have flat virtuals. And then we have what Monturov calls free knots. And free knots are the same as flat virtuals modulo the z move. And the z move is this, that if you have a virtual crossing next to a classical flat, this will be equivalent by the z move to the classical flat and the virtual on the other side. We saw this before because we saw that the Jones polynomial for virtuals, z up here, would have a crossing here and a crossing here, but here there's no under over. Um, but if you take knots modulo z moves, then you get free knots. And they are a little more elusive than the flats. And in fact, as Vasily likes to tell the story, Turayev, um, in his papers, essentially defined free knots, but he didn't define them this way. He defined them as knots defined by chord diagrams, maybe like that. Um, but the chord diagrams don't have any indications on them about orientation, order, over or under. They are just bare, uh, bare chord diagrams. And of course, you can form the corresponding virtual knot from such a diagram. Like from this one, we might label this crossing number 1, crossing number 2, crossing number 1, crossing number 3, 4, 3, that's 2, and here's 4. And so we would build someone who had Gauss code 1, 2, 1, 3, 4, 3, 2, 4. And I leave it to you to draw the picture, but it may have virtual crossings, and you take it up to Reidemeister moves. So you take bare chord diagrams up to Reidemeister moves on the chord diagram. The 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 completely bare combinatorial topology underlying everything. And they're very interesting also. So flat virtuals are somewhere in the middle of this. Right. Now, there was one or two other points that I wanted to make about this. One of them may be back on my other slideshow. I think it is, and I'll use it to save a little time. Just a moment. Oh yeah. Okay, here it is. So I wanted to show you another way to get some invariance of flats. Um, I'm going to talk about flat nautoids, and it occurs to me that I might not have told you what a nautoid is, so let's talk about that for a moment. You might have forgotten if I did tell you. If I've forgotten whether I told you, you might have forgotten. Yeah. Um, but a nautoid is a very good idea, due due to Turayev. A nautoid is a classical knot diagram, but it has ends. And the ends aren't necessarily in the same region. So this would be a nautoid. So would this, which is a more familiar object. And of course, you can have virtual nautoids if you want to, like that. Or like that. Virtual nautoids. One tangles is what these are usually called, just a classical knot with ends. And here is a nautoid. a proper nautoid, I might say. It's a classical, and the endpoints are in different regions. And in all cases, Reidemeister moves are not allowed to go over the ends. All right. So that means that with regard to the one I just drew, this would be a perfectly legitimate Reidemeister move. But something like this is forbidden. Right. And of course, the other allowances and forbiddens that we would use in virtual knot theory are the same. So, so this is a little like a virtual knot theory, but not quite. It's basically a kind of classical knot theory generalization where you have an open-ended gadget, but it has an ordinary knot theory associated with it. And one of the interesting things that we can do with nautoids is we can form the virtual closure. So, for example, if I have this elementary nautoid that I just showed you, then I can take it by virtual closure over to a virtual knot, which is obtained by taking these endpoints and connecting them any old way, but strictly by virtual crossing. Then by the detour move, it doesn't matter how I did it. So the virtual closure of this nautoid is the standard virtual trefoil, we called that. But every nautoid has a virtual closure, and we can easily prove that if we take nautoids to virtual knots, by virtual closure, then if k is equivalent here to k prime by Reidemeister moves, then k bar is equivalent in the virtual category to k prime bar. So you get all of virtual knot theory becomes a way of getting invariance of nautoids, and this is the way that that I and Nestle Hahn Gagumsu have been studying nautoids. So you can find some papers about that. In any case, it's quite an interesting subject which interrelates something almost classical with something virtual. And what I wanted to point out is that we can also think about flat nautoids. And we can map flat nautoids. This is an interesting point. We can map flat nautoids to nautoids. The way we do that is the following. Here's our standard nautoid, flat, excuse me, flat. Suppose we have a flat nautoid. Maybe a virtual, flat, virtual. and I want to mesh, I can do the same and use this mapping. Now, this mapping is not the one above, it's a different one. I'm taking it just to nautoids, and I'm going to do the following. I take the diagram, I take it to the descending diagram associated with it by starting, well, let's suppose it's oriented, so I know where to start and where to end. I start at the outgoing node, and I start drawing it so that it goes over before it goes under. And then this is invariant. This has the property that equivalent flats go by this mapping to equivalent nautoids. This is not hard to see if you play with the moves. You see, for example, think of a Rademeister 2 move. Suppose you're walking along here, but you bumped into what could have been a Rademeister 2 move. But you're walking along here. So as you apply the descending map, you go over before you go under, and then the other one ends up being a doable 2 move. So here's a doable 2 move, and it goes to a doable 2 move. So you see, we get invariance of flat nautoids by taking the descending diagram and choose your favorite invariant of nautoids and see what happens. So let me give you an example of the doing of that for getting invariance of flat virtual nautoids. So here's a flat virtual nautoid, the very one we were looking at before, almost, except I cut it, right? And here's my weight table for that. And here's my affine index polynomial for the descending diagram. So I take it over to its descending diagram and I calculate some invariant of nautoids. And the affine index polynomial works just as well for nautoids as it does for virtual knots. So there it is. And then I calculate the reverse, and I find that it's different, and I prove it's not equivalent to K-reverse. Now this is for the nautoid, not for the closed diagram. And these are the kind of techniques that we were used to. I was just taken by a little bit by surprise to realize how much power there was in just our weight table and ordinary flats. But these are some variations on the theme, and I wanted to mention them. Right. Oh, yes, katakami. If I am not mistaken, another way to formulate a consequence of katakami is that you can decide whether a flat virtual diagram is trivial by searching to reduce it. Um, Kawakami's theory involves the surfaces on which it could be represented, but as far as the diagrams are concerned, who can just simply try to reduce it. And remember what reduce means. A second Reitermeister move reduces like this. A first Reitermeister move reduces like that. A third Reitermeister move can be done in either direction and doesn't change the number of crossings. And then we have, of course, the possibilities of doing some other moves, like there is the possibility of doing this move, also not changing any complexity. And then we don't care, but we're always available. We can reduce like that. We can reduce like that, or add and triplet. And what you cannot do is that. Right. So that's what I mean. You can search for this. You can search for reductive moves. You don't have to make the diagrams any more complicated in terms of the number of crossings in the diagram. So if, for example, I look at the Kishino through the eyes of Kawakami, then I don't have to compute any invariance to know that it's non-trivial. I simply observe as I look at it as a graph. I say, oh, what do I have here? I have this, which is a three-sided region but can't be reduced. Three-sided region and can't be reduced. Four-sided region is not something I'm interested in. Here is a two-sided region, but it is an irreducible two-sided region, right? This is typical irreducible two-sided region, like that. So two-sided, not reducible, not reducible, not reducible, not reducible, and the outside is not reducible. So this is irreducible. See, Kawakami's theorem says if it could be reduced, it will be reducible by some simplifying moves or possibly some use of moves that would reveal simplifying moves, like doing a third move, but none of those are available. So this is absolutely an irreducible diagram. And many diagrams that you draw may be irreducible in that sense or reducible to an irreducible diagram. The um, the result is very striking if you've thought about the kind of examples that we thought about in our course, and that's why I thought we should mention this. Oops. Remember that earlier on we talked about examples like this one. I'll make it quickly. It's always worthwhile thinking about this problem all over again, this sample. But we talked about knots that had to be made more complicated before they could be simplified. And we also talked about the Dyanikov moves, where different of diagramming allows you to simplify on knots. But this diagram D is equivalent to the unknot, but needs complexifying moves. it has 10 crossings. It needs to be brought up to 12 before you can undo it. And that's the typical phenomenon in classical knot theory and also in virtual knot theory. But if we were to try to make a similar example, and of course you remember the reason was that the only way to get out of here and simplify it is to do something like swinging an arc. And this arc, you start to swing it, will end up increasing the number of crossings. There are no local reducing moves, and there are no three moves. It's a tight diagram, or hard to unknot, as we have said. Now, you could try to make a similar kind of device in the flat category. Maybe you try. You might say, well, I don't want to be able to swing the arc this way, so I guess I will just put some virtual crossings in that direction, and it can't go past virtual crossings, so that'll stop it. But now, wait a minute, I do want to be able to swing the arc. If I'm able to swing this arc, I can't have any virtual crossings. And then I'll be able to simplify things like a two move there. If I remove this possibility of doing a two move there, then I won't be able to swing this arc. And by the time I start watching the balance between those things, I end up producing a diagram which isn't trivial anymore. Well, that's what happens when you explore examples. But Katakami's theory about controlling genius gets you the result that that if you want to know whether is this, for example, a reduced diagram. Well, again, you can analyze it. Here's a two-sided region that can't be reduced. Here's a two-sided region that can't be reduced. Here's a two-sided region that can't be reduced. Two-sided region that can't be reduced. Here's a three-sided region, but it can't be reduced. It's got two classicals, and they can't move over a virtual. 1, 2, 3. Now this is available. So you have to think about it. You have to see what diagrams you can get from it and play around. So you have to do a little enumeration in order to find out that this is a reduced diagram. But you will find that it's just a matter of doing a little enumeration. Do that third Reidemeister move, look at the other diagram, find out that there are only a finite number of them and they're all reduced. So it's nice to realize that in this category, you can figure out that. The problem of whether two knots are equivalent to one another is harder, of course, and I'm not sure what the full answer is there. Okay. So now I want to talk to you about extending phonology to virtual knots and things. So let's look at an example and see what happened with the states. So suppose we took the virtual trefoil and we decided to make a Kovanov complex for the virtual trefoil. So there's the A state. Let's move that up a little. Okay, so put in the other states and take a look at what this would be like. So say I change this one. Oops. Change that one to a B. And we'll keep this one an A. Or we'll keep this one an A. And we'll change this one to a B. We'll make them both B's. Lots of Kauffman complex might look for some virtual knot. There will be states, and they will have loops in them. And everything that we did before, we can do. We can have a module associated with the loop, or in other words, we can label the loop. We can label a given loop, even if it's a virtual loop. We can label it with an X, or we can label it with a 1, and these become module generators. Like that. And these could be virtual. But there's a phenomenon that occurs here that it doesn't occur in the classical case, and you see it right here in this arrow. We started with one loop and we ended up with one loop. And over here we started with one loop and we ended up with one loop. Here, so these, I'll call them eta, they are maps from one loop to one loop. And that doesn't happen in classical knots. That you would resmooth a crossing and end up with the same loop they had. One loop from one loop to one loop. It has to do with the virtual crossing that can happen. Here we have a coproduct, and here we have a coproduct. So it wouldn't be hard for you to write down the modules. If we decide what we're going to do with eta and compute the Kauffman homology of this virtual trefoil knot. But does it work? We need to know that when we have a square, like this square going this way, or this square going this way, we need to know that it would either commute or anti-commute. Our original strategy is that we would make it commute, and then we would put the signs in order to make everybody anti-commute, so we would have a chain complex. But nevertheless, here's an example that we could go back to after we have figured out what goes on. Our question is, what do we do with the eta? So let's keep that example in mind and go forward. I want to give you an example. It's on a trivial knot, but it's nevertheless a good example. And so let's look at it. I'm going to look at the complex for this. From the A state. So those are the A smoothings, right? A. And then if I resmooth this way, it'll be a single cycle map. It'll be eta. And then I'll go here, and it's another single cycle map. On the other hand, if I do the other one first, then I will get now we'll get the lazy man's reward. Just use a small arrow there. And so what was that? That was a delta. That was a coproduct. Got two circles out of one, and there's a multiplication. Two circles go back into one. Okay. Now, now we're going to, we will choose eta is 0. That's one way of dealing with eta, is to just say it will be 0. It's not the only possibility. You can see Tubenauer, which I may be misspelling, his papers for another choice. And you can also see oh, sorry about that. I want to give you a reference name. Somebody's went out on my head. And see Rushworth for another approach. Rushworth's approach, if we do continue, I hope we continue a little later on, and with some more of this, I will talk to you about both this approach and Rushworth's approach particularly, which is very interesting for cobordisms. So there are some other approaches, but we're taking eta equal to 0 in this approach. All right. That means that, of course, that means that this is the 0 map, this composition. Now, what's going to happen when we compose on the other side? That's what we have to check. If it turned out that it's non-zero, then we would have to fix something or rearrange something. Well, let's see. Suppose that I have a 1 labeling this circle. So now I'm taking the 1 in the module corresponding to this curve. And I do delta. And we're doing this here. So you can think of the tensor product we have. Remember, delta of 1 is 1 tensor x plus x tensor 1. So I could, let me read other colors easier to see. That means I could over here have 1 tensor x, but I could also have x tensor 1. So this means I'm looking at the sum, and I have 1 tensor x plus x tensor 1. The 1 corresponds to this tensor factor, and the x corresponds to this other tensor factor, and this one vice versa. Then we apply m, and when we apply m, we add up. So we get x times 1 plus x times 1. 1 times x plus x times 1, which is 2x. It's not 0 unless our coefficients are z mod 2z. So we just proved something. Well, we didn't prove it, but I have an example, which is the essence of the proof. The Kauffman homology of K is okay for K virtual with mod 2 coefficients. So that's good, right? That's a good thing. It tells us that if we want to think about Kovalevich homology for virtual knots, we work mod 2, and then we have an extension of the mod 2 integral, the mod 2 classical, and we can think about these things. A good start, but we want to do better than that. We would like to get it over the edge. And I'm going to show you one way to think about doing that. The person who masterminded getting this over, there are two people actually who masterminded getting this over the integers. Those people are Manturov and also a bit in the background, Vero. Manturov, you'll see everything is on the archive. You find it all, and I'll explain that this is the way I'm telling you about it is related to work that I did with Heather Dye and Aaron Kessner. But Vero formulated Kovalevich homology with integer coefficients using chord diagrams. And it's unpublished, but I'm sure he won't mind if I were to share, and I'll put it in the Dropbox, a very nice paper he wrote on it, but he never published it, about that. But I'm going to talk about it in the category of knot diagrams along the lines of Manturov with some modifications related to the papers that I wrote with Aaron Kastner and Heather Dye. So I guess I should say see also paper by Dye, LK, and Kastner. And then there are some more recent papers that are in process. And the more recent papers in process with Scott Baldridge and Ben McCartney and William Rushworth and myself, are about interrelations of Kovalevich homology with thinking about graphs and other issues. There's a lot of things we're having some interest in lately. And then there are some other recent papers of myself and A.G. Ogasa and Igor Nikonov, where we're thinking about homotopy types. So that's all sort of a bit turbulent and in process at the moment. But let's go back to our problem. Our problem is an elementary one in a way. We want to get it to cancel. So one way to get it to cancel would be to get one of these x's to turn into a minus x. So let me talk about that. Uh, I'm going to steal my own diagram, then write on it. Oop. Okay. So here's what we're going to do. Um, we're going to give ourselves a little more room. We're going to use local coefficients. So that the algebra on a state circle has location. And we'll try the following. This isn't the final answer, but it's a way of thinking. We'll try the following. That if you have a bit of algebra here, alpha, and you transport it over here, virtual crossing, it will acquire an involution corresponding to the virtual crossing. So every time you move a bit of algebra from one place in the diagram to another, it'll acquire an involution. So we're going to have alpha bar bar is equal to alpha. So the parity, the number of virtual crossings that you walk through, is going to control whether or not that bit of algebra got an involution applied to it. And then the rules for the involution are x bar is minus x, and 1 bar is 1. And it's linear on sums. So now I want you to watch what happens, only I'm going to start my algebra. Then there's going to be a matter of a base point, but I'm not going to worry you about base points just yet. I am simply going to try algebra and see what happens when I go through composing something. And then you'll begin to get the picture of why I would play with an idea like this. You have to watch the algebra very carefully now. So it probably helps to eliminate extra labor from these diagrams. so that we can track what happened. All right. So I'm going to start by doing delta, and the delta occurred here, right? This is where delta occurred. So I'll put a 1 there to remind myself that the algebra was located right in there. Yeah, right in there. And then that means that new algebra, the x tensor 1 and the 1 tensor x, is located at this point in the image diagram. But now these have to be transported to the next site. These have to be transported, let me use a color, to the site where we multiply, which is up here, right? So we co-multiplied and algebra lives here, but the site at which multiplication occurs is up here. So these have to transport. The x transports with no involution. The 1 transports with no involution. This 1 transports through a virtual crossing and ends up here, but 1 bar is equal to 1. And this x transports through a virtual crossing and becomes x bar. And then we multiply here. Multiplying here means, well, these are the ones that were paired with one another, the ones on the right. So we get 1 times x bar, and we get 1 bar times x. So then what happens is that over here, 1 times x bar plus x times 1 bar, because you see only the x bar, only one of these got involuted in a non-trivial way, and this adds up to minus x plus x, which is equal to 0, and we're done. That is to say, we got the zero map. We got the zero map. This is great. So shouldn't this idea work? Maybe we could get this idea to work and just count the number of virtual crossings that we go through. Well, unfortunately, it doesn't work so well. But it's got the right idea in it. You will find if you, and I think it wouldn't be a great idea to go through counterexamples to this process here exactly, but it doesn't quite work out so well to get definitions to work in general to just count virtual crossings. I'm not entirely convinced that there is a way to just parodies of virtual crossings, maybe a little more subtly than this, to make it work. What I would like to do is to resolve this. I'm going to show you the way we end up solving it. But I would like it to be solved in such a way that all of the diagrams commute, like this one did, and that we only add signs afterwards. That would be nice. But we haven't quite solved that problem. So I have to back up now and tell you how we do this in a little more systematic way so that it can be globalized. But I think you now see the idea. And we have another 20 minutes or so. It's probably worth the rest. But my real message to you would be read the papers because it's a little intricate and probably not so easy to explain um, at the blackboard the rest. And on the other hand, if you did try to think about this, you might by taking this idea and moving it forward on your own, find a better solution than Monturov's and ours. But let's see. let's go back now to a classical knot diagram. And suppose that I consider what I call source sync orientations at a crossing. Now, such an orientation has some advantages aside from the fact that it looks weird, because you can smooth it this way and you get an oriented smoothing, but you just as well smooth the other way and you get an oriented smoothing. So a source sync orientation is a nice local thing to have. So let's try on our classic diagram to produce a source sync orientation. These go out, these go in. Now we'll try to make it work. So this goes out and comes, now it's in, and these would be out. I made a mistake, yeah. These are out, these are in. Out, in, out, in. No problem, worked. Exercise for you. Every classical diagram has source sync orientation. Well, what about a virtual diagram? What would happen there? Well, let's see. We tried this just so we did. All right. Out and in and out. Yes, that's fine. But now as we go along the virtual, we get a collision. And as we go along this one, we get points. Points are places where either this or this. You have an inconsistency of orientation on an interior point in the diagram. But of course, you see it's related to the fact that there's a virtual crossing there. We reverse something virtual crossing. And I could have said, well, I'm making this into a virtual crossing. And when I make it in virtual crossing, then I see that indeed there are cut points because this is regarded as a conflict because it's not regarded as a crossing anymore. So the two cut points that you saw are exactly the consequence of the virtual crossing. So counting virtual crossings should be like counting cut points. And we could say, all right, so the idea of counting virtual crossings can be general to the idea of counting cut points in our diagram. And then we want some systematic of laying down points that work best for our purposes. And what's that going to be? Well, I'll tell you the conventions that we end up using. So here is a crossing. And let me get my conventions straight. So we're going to do it this way so that the orientations are chosen at a given crossing like this. And that is the same as saying that this is going to have a source sink orientation that looks like this. But this is out, and this is in, and this is in, and this is out. And another way of putting would be to say the following, that I'm going to put a cut point here, and I'm going to put a cut point here. If I do that, no, let me show you what I mean by that that convention. If I have this like that, and I put a cut here, point there, so that this looks like it was to begin with, and this looks like it was to begin with, then this will be going out, and this will be going in. And here is the cut point that contradicts it right then and there. And this now has the structure of this locally for its smoothings. So, so this may be the easiest way to remember this convention, that that at every cross we're going to be assigning cut points like this, and those will be the cut points for checking for counting the involution. So then we will have involution, and we will be watching an algebra element, and when it goes through a cut point, it becomes the bar every time you go through a cut point. And we simply can assign cut point, a pair of cut points at every crossing like that, which will produce this nice nicety of smoothings like that. So that's the first part of making the thing systematic. Is instead of what the virtual crossings, we use the real crossings and assign cut points at them by this method. So let's take a look at our original example and see what happened to it under those circumstances. There's our example. But I should go back one step. No, well, we'll copy this and work with it. Now we need to now go back to the diagram that it came from. Uh, I could have made my life a little easier, so I might as well do so by choosing the other orientation. Now, never mind the crossing structure over and under. We had said that put cut points here. And that would be our counting structure. And of course, you will notice that if you have two cut points in a row, then that means in, out, out, and for all intents and purposes, that's the same as no cut points at all. And that's why we want involutory structure anyway. So let's see what happened here. That means there's a cut point here, there's a cut point here, and there's a cut point here. Maybe in red? On double. Right. I got that one a little bit. Maybe we better put those cut points in blue on this one. Now let's see what our parity counting looked like if we're using this system. You see, the only question is what happened in here. But as you see, when things transport on this one, you have an even number. Everything's fine. When you transported here, you went through one cut point, and when you transported here, you went through one cut point, but it didn't matter. But the X had to go through a single cut, um, and um, and if the X had gone the other way round up to that site, it would have also gone through a single cut point. The parities are working out this way, and they don't depend on placements of virtual crossings. One reason why I don't want placements of virtual crossings is because we want things to be invariant under detour moves, and so virtual crossings can move around a lot, coming in and out. It's better to have the cut points controlled by the actual classical crossing structure of the diagram. But then these parity counts do work out this way, and that's the beginning. And there's one more problem that has to be taken care of, and that has to do with the order in which you write your algebra. See if I can tell you a story about that, and then that will be an introduction to this rather tricky definition. So let's go back to our involution structure. We have that a plus bx is a typical element in a module. This would be in the module associated with some circle. right? In the complex. Labels x, labels 1, and multiply, and sums like that. And we can, and if we called this z, then we could call z bar equal to a minus bx, of course, and um, and then um, and then you can notice that this behaves well. For example, if I take zw bar, what will I get? I will get a plus bx times c plus dx bar, which is equal to ac plus ad plus bcx, and x squared is 0, remember? Bar, which is equal to ac minus ad plus bc times x. And on the other hand, if I take z bar times w bar, I'm going to get a minus bx times c minus dx, which is equal to ac plus bdx um, squared, excuse me, minus bcx minus adx, and that's not there. And we got the same result. So we get z bar w bar is equal to z w bar. Um, so so this works nicely. The conjugation is working well. Um, and what about how it behaves under the operations? What do we have for delta of 1 bar? Well, delta of 1 bar is equal to delta of 1, which is equal to 1 tensor x plus x tensor 1, right? Um, and delta of 1 bar is therefore equal to minus delta of 1 bar. There's a change in sign. And what about delta of x? Delta of x bar is equal to x tensor x bar, but that's equal to minus x tensor minus x, which is equal to x tensor x. Um, and so this is, wait a minute, make a mistake. I'm sorry. I'm claiming that if delta of A is equal to the some summation of first pieces and second pieces, then I'm claiming that delta of A bar will be equal to minus the sum of A1 bar tensor A2 bar. So let's see if we agree with that for delta of x. So if I take delta of x bar, then I'm looking at delta of, oh, I see what I did, delta of minus x. But delta of minus x is minus delta of x by definition, because it's extended linearly from its basic valuation. And that's equal to minus x tensor x. And that, of course, is also equal to minus x bar tensor x bar. And so you see that's correct. All right. So we have this behavior with respect to the coproduct, that delta of a bar is equal to minus the sum of the bars. And delta of one bar is equal to delta of one. So keeping that in mind, we then, in order to make things work, we need to be able to take a source sink. We need to be able to take a given source sink and change it and still get invariance. And this leads to, in the sense of being able to replace it by something like that. This leads to the need to order the whole complex so that in a given order, x tensor y is replaced by minus y tensor x. And the squares are then designed to anti-commute. And you get a chain complex. I've decided I'd best just summarize. All right? So in the end, in order to the whole thing compatible with the way the involutions work, we need an extra non-commuting. We need to essentially make the whole complex into a Grossman algebra, and we the involutions, and then it turns out to all fit together. You get a Kauffman homology over the integer. It extends the Kauffman homology for classical knots. As I said, this feels like it could be better, but it has been very difficult for us to understand how to make it any better than it is. So, at another point, when we have more time and go more slowly, I'll show you how it works in more detail. But let's just take 5 minutes now to look at the picture of what we want to generalize a little bit, so that you get a picture of where this would go. I feel like I drove you in technicality there, and I'd like to leave you with something, some larger picture. So recall when we were general theory or general theory of how phonology works, we found that with the Frobenius algebra that's more general like this, and that I told you that x squared equals turned out to be another good idea along with x squared equals 0, but you change the coproduct when you do that for x. And that turned out to give another homology called Lie homology, and those two interact Kovanov and Lee interacted with one another to give some very good results. And now I'm talking about classical work, and it does get generalized to virtuals. So with Lee's algebra, you have a situation, but the grading is not preserved. So when you form the boundary of something, the J part of the grading changes, and you get to measure how much the grading changed in relation to what happened with Kovanov. And this turns out to actually give very interesting topological information. The Lie algebra can be made prettier by rewriting it. Remember, the Lie has an x, and it has x squared equal to 1. And if you write r is equal to 1 plus x over 2 and g equal to 1 minus x over 2, and rewrite the algebra, then you have r plus g is 1, r squared is r, g squared is g, r and g multiplied is 0, and the coproduct of r is 2r tensor r, and the coproduct of g is 2g tensor g. And this is very pretty way of thinking about this algebra. It means that you can write down a lot of cycles in this Kovanov homology by labeling the states alternately with red and green. Because you see, if you multiply two of them, so a state like the one I'm drawing here is a cycle, because all sites are multiplication sites. And when you multiply, you get 0. So the boundary is 0, and you can produce lots and lots of cycles in the Lie homology and figure out what all the cycles are by thinking about smoothing that can give you patterns of colorings that work right to give you cycles. So this means that the Lie homology is easier to compute, but the way it behaves in the filtration is subtler. And so it's possible to compare Lie homology and Kovanov homology and use the two of them to get information. And that's what Rasmussen did. So Rasmussen compares Lie and Kovanov homology with each other and looks at the way the depth of filtration works and gets an invariant. And his invariant was able to, and here I'll just skip to the result, it was able to, for example, show that the four-ball genus of a torus knot of type AB is actually equal to its Seifert genus in the 3-sphere. It's equal to A minus B 1 times B minus 1 over 2. And this comes out of this playing around for Rasmussen. It comes out of this playing around with what is the filtration like in the Lie homology cycles in relation to the Kovanov homology cycles. And of course, I'm not going to say more about that since we're at the end of our time, but this is in itself worth understanding, worth going through more slowly to understand, and then to see how it does indeed generalize to virtual knots and gives us a similar kind of result. It gives us a result that says that a positive virtual knot has its four-ball genus determined by its virtual Seifert genus, which I described to you a while back. So we can't do anything at this point but be sketchy about this, but I look forward, if we can find the time, to taking it very slowly and going through these constructions with you and myself to show you how this situation manages to work itself out. So stop the course at this point, and I thank you for all your attention and all your time.
Thank you very much. Thank you for this nice course. And what do you think? Would you like to continue about virtual knots and Kovanov homology in next year?
Yeah, I'd be happy to. It's, of course, to your scheduling what would be a good time. We could continue on Friday nights for me and Saturday mornings for you if you want.
Yes.
And then